Find the area of the region trapped between y equals x cubed minus 2x and y equals x squared. All right, so the issue that we have in this particular problem is that these regions change which function is on top and which one's on bottom from within the interval that we would need to integrate. And the interval that we would need to integrate here is any place where we can see a finite bounded region, we need to include that. So for instance, right here is a finite bounded region, and right here is as well. So we would need to integrate between this point right here where x is -1 up to here where x is 2. So we need to integrate between those two particular values. Now, the thing is, if I integrate with, well, in case you aren't aware, I've color-coded these functions. So you should be able to tell that this is the shape of a general polynomial graph. So it's going to be a cubic. And the other one, of course, is a parabola. So the red curve there is going to be the y equals x squared. All right, so I've color-coded them for that reason. Now, here's the thing. If I integrate across the entire interval, this little portion, if I use the cube as the upper function first, this little portion would be positive, and then this region right here would end up being negative because the square function is on top. There's no real way around it. What we have to do here is we have to split this up into separate subintervals. Now, from the graph, it might be obvious where these things overlap, but it might not. So I'm going to show you techniques that you could use here. I think in this case it's pretty straightforward that this is going to be at 0. But if you want to find out where curves intersect, you can always solve for intersection points by setting your curves equal to one another. So x cubed minus 2x is equal to x squared. As long as both of these functions are solved for x or y, just depending on the problem, then you can just set them equal to each other, and that's fine. Wherever this equation has zeros is where we're going to have intersections. So let's try it out and just verify, even though we already know what these are. So x cubed, if I subtract x squared from both sides, I would have minus x squared minus 2x equals 0, for which I could easily factor out an x, leaving me x squared minus x minus 2 equals 0. And that should factor, let's see here, x and x, 2 and 1. If this is negative and that's positive, great. Then when I set each of these factors equal to 0, I get the zeros of this polynomial being 0, positive 2, and negative 1. So just like we're seeing here. So we have a intersection here, here, and finally here as well. Now, just knowing those intersections isn't really enough to know exactly how to set the problem up. We also are going to have a picture of the graph so that we can see which function is on top and which one's on bottom within each interval. So here the graph was provided, but if it wasn't, that really is an important part of working these problems out. So you want to make sure you have a picture of the graph, location of intersections, and then start into determining the area that's trapped between. Now, graphing on your calculator, or just providing a graph, that should be fine. That shouldn't be a problem for you, especially when the graphs are in functional form, y equals some function of x. Of course, you would just go in, enter your function, and make sure your bounds are set properly so that you can get a good picture, and you're all set. So that shouldn't be a problem. There we go. Now, if the issue is determining intersections. So generally when you're determining intersections, unless these things happen on integer values, which isn't always the case, you might have to do a little bit of solving to figure it out. Now, students will often get intimidated by solving cubics here. Now the one I had was fairly easy because there was a common factor of x from each of these terms that I could just factor out, which left me a quadratic and I could solve from there. Now if that wasn't the case, if this wasn't a polynomial that I could easily do that, like if there was a constant term here, one thing you can always do, of course, is graph the function. So just assume, get it set equal to 0 and assume it's a function. So just call it f of x. All right, if we graph it, then the graph itself, let me zoom in, and a good way to zoom if you can see on screen where zeros are occurring, you can use the box zoom. It's the very first item under the zoom menu. It allows you to place a corner in one position of a box on the screen, and then you can drag your rectangle. It takes me a moment here because I have to keep repeatedly pressing this button on screen, but it's a little easier for you all with an actual button. So anyway, now I'm going to reset my screen and see only this portion of the graph, which makes it a little easier to see the zeros. So even if I am unable to factor this, I can see the zeros of it at -1, 0, and 2, and the zeros are the solutions to the polynomial. So that's another way that you can get intersections if you're just not sure how exactly to solve those kinds of equations. So the area here, we would need to do an integral first from -1 up to 0. And in this interval, the cubic is on top. So it would be x cubed minus 2x and then minus x squared dx. And then we need to add to that the area of this region, which is trapped between 0 and 2, but the square function is on top. So it's x squared minus the quantity x cubed minus 2x. I didn't need to put parentheses around the x squared here because it was just a single term. Whenever there's multiple terms, you need to subtract the entire quantity. And that's just ensuring that the distributive property will have this negative distribute to both pieces within the polynomial. Okay, so that right there, that can actually just be put into FNN. So if I just bring up the calculator, we can get started. It might take a moment to type this in, but we're going from -1 up to 0, and then we have x cubed minus 2x minus x squared. Oops, I got 2 x's there for some reason. Okay, and then that's integrated with respect to x. Then I'm adding to that another integral from 0 up to 2 of x squared. And I could use these parentheses, or I could just mentally distribute that negative, whichever is better for you. It's fine by me. I'm just going to go ahead and distribute that as negative in my head. All right, and there's my second integral. Now I'm ready to calculate. All right, and I get an answer like this, which I can change to a fraction using the conversion in the calculator. So 37/12. So we get 37/12 from FNN. Okay, now in terms of what's expected for these types of problems on exams especially, you're often going to be asked to possibly provide a graph for supporting evidence, what the intersection points are for supporting evidence, and what the integral that got you to the answer. Not just the answer. And the thing is, it's more a protection for you than anything else, because the thing is, if you have this question and all you do is answer 37/12, okay, that's the right answer, great. Now, what if you end up coming up with like 45/12, and that's all you've provided? Well, you get the entire problem wrong, because, well, it's the wrong answer and you don't have any supporting evidence of it, so it's wrong. And honestly, some instructors will give, even if you have the right answer, if you don't have any supporting evidence, not give full credit. So it's really kind of up to the instructor there. So it's always best to have some sort of supporting evidence, and you can have that on scratch paper, or there's different ways that you can insert that sort of thing in the homework. Let me show you one way you can do that. Okay, so I'm in creating a message, and I can use it here, or this is the same kind of edit box that's provided in the discussion boards, all through XYZ, which is kind of nice. Now, of course, you can just type text, sure, but when you're typing a function like x squared plus 2x plus 5, yeah, it looks okay. But what about a square root? So then maybe you could type in, who knows, f of x equals the square root of x plus 7. And, if you're trying to express ideas to other students or to the instructor, that gets the point across, but there really are better ways of doing this sort of thing. And it's really very easy. So one thing you can do, these last 3 buttons, you've got add new math, math symbols, and add edit graph. Add new math, if you happen to know how to do LaTeX, mathematical equations, this is perfect for you. You basically just start a set of backticks, and you can type in pretty much any kind of basic mathematics. And actually, let me just put the f of x on there as well. And it will render it for you in place and make it look nice, make it look like what it's supposed to look like. So that's really a great feature. Now, you might be thinking to yourself, what if I don't know what the symbols are for all those things? And I would totally understand, because there's a lot to know. That's where you go to math symbols. And it's just an open palette for all the different things that you can pretty much want to do. You've got fractions, exponents, square roots, nth roots, derivatives, limits, summations, integrals, and all kinds of things here. Anything you probably need is probably here. So let's try an integral. All right, so when you press it, it comes up like this. And this is the LaTeX form. And so if you click away from it, it'll show you what it renders as. But then you click on it again, and it goes back to the editing mode. So you can kind of see like the a and b that are the endpoints of the integral. So even if you don't understand what this underscore is doing or the up arrow is doing here, you can see that a is lower bound of integration and b is an upper bound of integration. Oh, great. Okay. F of x is the function that you want to integrate. So you could just replace that with who knows, let's say x squared plus 2x minus 5. And there you go. You've provided an integral that's very human readable for other people. So that's great. That's one thing that you'll want to be able to do. Because if you're working with each other in the discussion boards, you want to be able to express ideas easily and not have to upload scratch work that you have to take pictures of and save and that sort of thing. In addition, we have graphing capabilities. So you can hit this add edit graph, and it works just like your graphing calculator. So for instance, if you need to, this is your functional graph, y equals f of x, and you can put any kind of graph you need in there. So let's just say x squared minus 5 You can change what it's graphing between, but if you leave those blank, it's no big deal. And there's all kinds of different options here, but if you don't change any of these and you just come down here and hit Add Graph, look at that, you've got your graph. All right. If you need another graph, what you would do is just hit Add Graph. Oh, I think actually you just come through and start a new one. So let's say we have 2x minus 4. Let's hit Add Graph again. All right, there we go. So now we have two graphs on the same axis. And if you need to edit any of them, you can go through and edit. You can remove. I accidentally got two of the same one there. No big deal. And you can get a nice looking graph, and then when you're done, just press Insert. Or actually, there's parameterized graphs as well. You might need those on occasion. If you need to add a parameterized graph, you can easily do that. So like this one defaults sine t, cosine t. You can put, again, bounds on those functions, but if you leave those blank, it will just pick something that seems to work. But when you're all done, just hit Insert, and you've got a nice graph showing up in your message or discussion post or scratch work for a test. So now, if you don't take the time to learn these features, it's not really a huge deal. We'd never take off credit for that on a test, for instance. But you'd want to make sure that you are able to scan in your scratch work and supply that scratch work at the end of your exam. So these things are just a little bit more efficient.